This is the last section for this unit. It's not terribly difficult. I'm basically just trying to get a concept across to you. There are no equations in this section, although there could be. We're just sort of going to go for the concept in this case. So I imagine that at least some of you have heard the term buffer before. Buffer is another chemical term that gets used out there in the real world a fair amount. Basically, the idea behind a buffer, I'm going to sort of set it up by describing the bloodstream in a little bit. So there are a lot of biological systems. The classic example is the bloodstream that need a very specific pH to work properly. If you remember in the previous section when I was showing the pH scale, I said the pH of blood in humans is slightly more than pH 7. It's about pH 7.3 if I remember correctly. And basically, your blood needs to be right around pH 7.3 to work properly. If the pH of your blood deviates too much from that pH, your blood basically stops working and you will end up dead. So if the pH changes too much of your blood or any other biological system, the system stops working. So if your blood stops working, obviously you're going to die. So the problem is that your blood needs to keep the pH right around there. It does not want to deviate from that pH. So your bloodstream actually contains some chemicals in it that prevent major changes in the pH of the blood, because if there are changes in the pH of the blood, as I mentioned, it can have lethal consequences. So you can ask, and this is a perfectly valid question to ask, well, why is the pH of the blood going to change at all? Who needs these chemicals in there? Wouldn't the pH just always more or less stay the same? The reality is that that is not true for a number of reasons. The problem is that when you eat food and when your cells perform respiration, the food that you eat a lot of it ends up being dumped into your bloodstream. And the food that you eat can alter the pH of your bloodstream significantly. When your cells perform respiration, when they produce carbon dioxide, and the carbon dioxide is dumped into your bloodstream to be transported to your lungs to be exhaled out of your breath, the carbon dioxide can also significantly alter the pH of your blood. So there are these things that are constantly being dumped into your blood, either from things that you eat and drink or from things that your cells produce, that are being dumped into your blood that could change the pH of your blood with lethal effects. And so your blood basically has to prevent those things from changing the pH too much. The way that your bloodstream does that is that your bloodstream has certain chemicals dissolved in the bloodstream that don't stop the pH from changing at all, but they prevent the pH from changing significantly. They prevent the pH from swinging too wildly. Those chemicals that are dissolved in your blood are called buffers. However, those are a specific type of buffer. There are buffers that are found in other tissues in your body. There are buffers that are found out there that are man-made in the real world. If you have a swimming pool, or if you have ever used a swimming pool, you may be aware of the fact that the acid that is associated with rainfall. So rainfall is commonly somewhat acidic. If you have acid falling into your swimming pool, it can change the pH of your swimming pool significantly and affect your ability to swim in it, affect the ability of certain microbes to grow in it. And so you actually need to have chemicals dissolved in your swimming pool that also prevent radical changes in the pH, in the acidity of your swimming pool. And those chemicals are also called buffers. So buffers are basically any material that is dissolved in a liquid that is used to resist the change in pH. And I'm emphasizing the word resist here because it's not as though buffers completely stop the pH from changing. They just slow down the change in pH. And so basically buffers resist the change in pH when an acid or a base is added to a solution. And if you didn't have a buffer dissolved in a solution, then if you added acid or base, then the pH would swing much more wildly. It would change much more than if you had the buffer dissolved in it. So Again, you don't need to know this in any excruciating detail, but a buffer is usually made of a weak acid and a conjugate base, or a weak base and a conjugate acid. And the idea is that if you have an acid and a base mixed together, then they will prevent other acids and bases from they will basically sop up or donate protons and prevent the pH from swinging too wildly in a solution that they're dissolved in. But again, I'm just sort of putting this here for those of you who want a little bit more detail. You don't really need to know this, in my opinion. And there's much more to know, but you can stop basically at bullet point one. I would like you to know this. Buffers are not just found in blood, they're found in pretty much all biological systems. Your cells need specific pHs to work properly, and because of that, your cells have buffers dissolved in them as well that resist changes in pH. We use buffers in the real world. One of the examples that I gave was swimming pools. But there are other situations where that's true as well. I'm pretty sure that laundry detergents and other things like that have buffers dissolved in them as well. So that is it for the unit. These are some questions that you may want to work on. However, I will post a more detailed list on the Blackboard website. So that's it for Unit 8, and I will see you on Unit 9, which I believe turns out to be Chapter 6.